At the beginning of the 20th century, Albert Einstein radically changed Isaac Newton's understanding of the universe. According to Newton, time and space were separate from each other. Time was universal, progressing in the same way everywhere. Space, on the other hand, was a fixed stage of events within events.
However, Einstein changed this understanding with his theory of special relativity in 1905.
According to Einstein, time and space are not separate from each other, but united. This united structure is called spacetime. This structure has 4 dimensions: 3 spatial dimensions, x, y, z, a temporal dimension, t or ct, combined with the speed of light. The mathematical description of this unified structure is known as Minkowski space, in which events are described by 4-dimensional coordinates x, y, z, ct. The distance, spacetime interval between these 2 system events is given by the following equation. This formula proves that space and time are now a single structure. Time is not independent of space. If space changes, time is also affected. This directly means that if space is curved, time is curved too. This basic information is important for us to understand the functioning of black holes, because black holes affect not only space but also time. In other words, they exist in a 4-dimensional spacetime curvature, not in a 3-dimensional structure. Einstein's theory of general relativity, proposed in 1915, is a revolutionary theory that explains how mass and energy can bend spacetime. According to this theory, objects with mass and energy bend spacetime around them. In other words, mass affects time and space, and this interaction directs the motion in the environment where the object is located. General relativity states that spacetime, which connects space and time, is curved due to mass and energy. This curvature changes the geometry of spacetime, and this change determines the motion of the object. Einstein's famous field equation expresses the relationship between this curvature and mass energy as follows. This equation mathematically shows how mass and energy can bend spacetime. The greater the mass, the greater the curvature of spacetime. This curvature even affects light rays, forcing them to take a different path. Black holes are the most intense points of curvature in spacetime. They are so dense that they bend the spacetime around them so much that nothing, including light, can escape from this region. The event horizon around a black hole is created by the large curvature of spacetime caused by mass. This curvature is so strong that space and time become entangled. The time dilation experienced by an object as it moves toward a black hole is another example of time warping. That is, as an observer approaches the black hole, time slows down and the passage of time changes dramatically. Black holes can be explained by a special solution of the equations of general relativity. In 1916, Karl Schwarzschild found a solution to Einstein's field equations. This solution shows how spacetime is curved for a spherically symmetric and stationary constant mass object. The Schwarzschild solution is used to explain the spacetime geometry of a black hole. The equation form of this solution is. This equation shows how spacetime around an object of mass m is curved or bent. Note that it is into parts. This is a direct proof of the working together of space and time as we approach the black hole. When r gives to gm, ca, time stops, event horizon. At the same time, the measurement in space approaches infinity. There is a certain radius around the black hole. This value is called the Schwarzschild radius or event horizon. Inside this boundary, no information, not even light, can escape. This solution shows that the effect of the black hole goes not only to space but also to time. If time is curved along with the existence of space, the system is not 3-dimensional but 4-dimensional. The Schwarzschild solution is one of the strongest proofs that spacetime is 4-dimensional. It is the mathematical proof of Einstein's idea that space and time are unified. When spacetime is curved, objects and light move in curved paths, not in straight lines. because the straight line in the universe has now changed depending on the curvature of spacetime. As we approach a very dense fountain, such as a black hole, time begins to flow more slowly. This shows that not only the spatial part of spacetime is curved, but also the temporal part. If r gives rs, that is, the event horizon is approached, t0 gives 0, time almost stops. In classical 3D space, we could only bend the x, y, z coordinates. However, here, since time is also bent, this event cannot be explained with just 3 dimensions. The structure affected by black holes is 4-dimensional, space x, y, z plus time t. Mass like black holes affects not only space but also time. Therefore, the structure that is formed is not just a 3-dimensional space, but a 4-dimensional spacetime curvature. As you move towards the center of a black hole, the curvature of spacetime increases. Eventually, a singularity forms at the very center of the black hole. A singularity is a point where spacetime becomes so dense that the laws of classical physics cease to apply. In other words, space and time lose their meaning here. This point is defined mathematically as r equals 0. This is right inside the event horizon of a black hole, known as its Schwarzschild radius. Up to the event horizon, light and everything else can travel in time. But at this point spacetime has already collapsed. Mathematically, we can observe this situation according to the following equation. When we examine the relationship between rs and r equals 0 in the Schwarzschild solution, we can express how spacetime collapses as follows. Singularities defy the laws of classical physics because there is infinite density and infinite temperature. That's why the singularity at the very center of black holes is so important for understanding a 4D structure. It shows how space and time collapse and merge together. Black holes have an important place in the world of physics. These huge and mysterious structures help us understand the nature of the universe, both theoretically and observationally. Research on the 4-dimensional structure of black holes, the bending of time, gravitational waves, and the internal structure of black holes will allow us to understand physical laws more deeply.